Hello and welcome to Beamer, folks. I thought I would just show you the original circuit that we developed for the current sync device, and you can see it there. And we've removed the base resistor of Q4. If you remember, we changed R3, which is a 10K, to a 10K potentiometer, and this effectively is an NPN configuration on the output here with negative feedback in unity gain. Now I go to the source circuit, which effectively is a PNP output configuration, but all the rest is basically mirrored, and as it were, let me lift it back up to here, as it were, it rides effectively on the compliance voltage of 12 volts. You have exactly the same configuration here, to the point that 4.7 volt Xena, you've got that reference voltage split by a series network here, ending up with R8 being 10K. The voltage across 10K is 0.96 of a volt. You've got got an op amp, and the op amp is of course the other op amp in the package of the TLO72B. The output transistors Q1 and Q2, as you can see, are PNP devices, the output being BD140. The 0.96 volt DC should produce a 9.6 milliamp current flowing through R10, which is a 100 ohm resistor. The ohm sign on this CAD program always is a rectangle rather than an ohm symbol. It's a bit odd, but once you get used to it, it's fine. The load, of course, it's a source, and the load is an LED load, which is D4, and the load is taken from the collectors of both Q1 and Q2 junction through down to 0 volts. So if there's 9.6 milliamps flowing through this 100R resistor, you've got 9.6 milliamps always flowing through here. The explanation of the feedback system is identical to the sync. You've got a unity gain negative feedback loop here, and say for example, if this voltage here, which is of course 0.96 of a volt across 100R, were to go down, the negative input of IC1 would also go down. The output here, which is at pin 7 of that op amp, would go up. The emitter of Q1 would go up, and therefore the emitter of Q2 would also go up, compensating for the downward motion of the voltage there. So therefore that's a definition of negative feedback, isn't it? The input is voltage selected on the positive input of the op amp on pin 5, and if we were to replace R8, which is a 10K resistor, with a 10K pot, we should be able to move with the center wiper of the pot between 0 and 0.96 of a volt, representing 0, and that's mirrored to R10, and so therefore that should be adjustable from 0 to 9.6 milliamps, effectively creating a load current here of 0 to 9.6 milliamps, no matter what you put on by way of a load at this point here. If you were to use a resistor, again, the resistor value, if it got too high, is limited by this compliance voltage of plus 12 volts. Okay, so all that remains for me to do is to implement this diagram in a practical circuit. So that's the next thing I'll do. Well, here you can see the practical implementation of the source circuit. The only difference to the circuit diagram is in the negative feedback loop here, I've put in a 10k resistor to balance the null system of the op-amp. This circuit, being a source circuit, of course, is riding on the compliance voltage of plus 12 volts. And in respect of the sync circuit, it seems pretty obvious that this should actually work. But does it? Let's just check the reference. Now, I'm checking from the compliance voltage of plus 12 volts, and I'm getting, switch that down to there, I'm getting minus, that would be 4.756. So the reference voltage is working perfectly okay. I should be getting again 0.96 of volts DC, this time across R8, which is the junction of the series resistor R7 and R8, producing 0.96 of a volt from the reference. And this should be saying 0.96, and indeed it is. Now, if I go to the emitter resistor of R10, that's the emitter of Q2, R10, the 100R, and as I don't know whether you remember, but it is the range resistor position. Now, if I measure the voltage on there, which is across the 100R, I'm getting 0.943. Well, that's a little odd, a bit suspicious. I haven't got the LEDs connected to 0 volts yet, and let's just connect them up and see what happens here, and see if this corrects itself or whatever. Okay, that seems to be running quite nicely. Now let's check the voltage across R10 again, which should be 0.96 of a volt, producing a 9.6 milliamp output current. And look at that, I'm getting 0.2 of a volt. Well, that's very odd. I think I know what's going on, but do you? Of course, the reason is that the op-amp TL072B is not a true rail-to-rail op-amp. It can work close, if not slightly negative, to the negative rail, as was clearly demonstrated in the sync. But as far as the source is concerned, the positive voltage of the IC1, which is pin 8, really wants to be higher than the compliance voltage. You can do that with an auxiliary power supply, but the power supply kind of needs to be tracking. You could do it via a battery or a cell, just lifting it above the compliance voltage of plus 12 volts, making it a slightly higher positive. But I have another solution which I found works, and the next thing I'll do is adapt the circuit slightly so that it accommodates that solution. Now here is an implementation of my solution. I don't know whether you can spot what I've done here, but I've put a diode in series with the supply and placed pin 8 to the anode side, the input side of the diode. So the circuit, the compliance voltage, gets dropped by 0.7 of a volt, lifting the supply to the op-amp by that 0.7 of a volt. And let me just go through that again and check the reference. The reference voltage is 4.742. Going across now R8, which is the 10K, I'm now getting 0.96 as designed, and now I should get 0.96 across R10, and lo and behold it is. There's 1 millivolt lifted there, but we can accept that, and that will produce 9.6 milliamps through the LEDs. I put a piece of paper across the LEDs. I was finding them so bright it was dazzling my eyes. I'll now replace R8, which is the 10K, with a potentiometer and just see if we've got proper control from 0 to 9.6 milliamps through R10, and of course coming out of the joint collectors of Q1 and Q2 and the load. And that's what I'll do now. I've now got the pot in situ, and we're getting obviously LED current there. I'll check the voltage across the pot. Of course, the potentiometer resistance is not as accurate as the 1% resistors I'm using here, but let me just check what the voltage is across there. There it is. It's 1.059, 1.06 of a volt. Now if I go across R10, it should be the same, and it is 1.06 volts. Now I should be able to adjust this potentiometer down to 0, so we get 0 volts across R10, and let's see how that goes. Okay, starting to drop, 0.90, coming down further and further, further and further, 0.6, 0.7 of a volt that is. Going further and further, down, 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 further, further. Oh! That suddenly dropped out, and I'm not fully down on the potentiometer. And just to demonstrate that, I don't know whether you can see, but let's see how much to go. Wow, I would say it's about a quarter of a turn. So there is a dropout before the potentiometer gets to quarter of a turn towards the compliance voltage. Now, obviously what's happening is that the op-amp is still not under proper control. It's still unable to control the voltage linearly across R10, and that is indicative that the supply voltage to the op-amp on pin 8 is still not high enough to maintain control. So I have a solution for that. It's pretty obvious, and that is to whack another diode in the supply, therefore producing a 1.5 volt drop and placing the op-amp 1.5 volts DC above the compliance voltage, and that's what I do now. Hopefully you can see now that I've added a second diode in series. These diodes would have to be rated well above the maximum current that you would want to draw through Q2. So they would need to be maybe 4 or 5 amp diodes, but that is producing 1.5 volts drop, and I've got the positive side of the op-amp IC1 pin 8 through to the anode of the first diode, so therefore lifting it above 1.5 volts. Now I've got the meter set across R10 again, and I'll adjust the potentiometer. We're reading 1.06 volts, so let's drop down a range. There we are. Now again I'll do the linear drop down, a linear drop with a rotational pot. Okay, there we go, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1 and 0. And 0 is exactly 0 on the potentiometer. If I lift the potentiometer very slightly, you can see it lifts the volts across R10 very slightly as well. And there we are. So that's now the circuit operating. You could lift this op-amp via perhaps a cell, 1.5 or maybe a 3 volt cell, and that would be raised above the compliance voltage of 12 volts. And incidentally, I've adjusted the 12 volt supply. In fact, it's running here by the looks of it about 13.5 volts, nearly 14 volts.
because I wanted still 12 volts across the compliance voltage. So that's it. Finally, I'd like to add that with a current source, it's always worth bearing in mind that with a very large resistance, the voltage on the output will always be at the compliance voltage initially. This can be a bad thing if you're running semiconductors or circuits that require initially a low voltage that doesn't go to the compliance voltage. If the load is very light, the constant current will attempt to always drive the output up to the compliance voltage, and whatever circuit you might have might not agree with that higher voltage. It might blow your circuit up. So it's always worth bearing in mind with a current source, it's good to have adjustability on the compliance voltage so that you know exactly where you are and you're not going to cause damage to your load.
This is Beamer signing out for now.